So we're going to talk about mass moment of inertia in section 17.1. And let's start off by recalling that we have the second law of force equals mass times acceleration. So this means that if we were to divide force by acceleration, that the larger our mass is, the less acceleration we get for a given amount of force we apply. So it's a measurement of resistance to mass is kind of like a measurement of resistance to acceleration. And that's in a translation type situation. But in rotation, we're going to have a situation where we'll have a moment, and this moment equals I times the operated on the angular acceleration. So if we do the same thing, if you look at the moment divided by I, you see that the moment of inertia really is, the mass moment of inertia really is a measure of resistance to angular acceleration. So this moment is really the second moment of mass about an axis. That's the more mathematical definition of this. And the mass we're talking about here is a differential mass initially. Let's draw a little image of this. So we have our differential element of mass, some distance r from an axis. We then can write I equals the integral of r squared dm. Now dm, differential element of mass, is just equal to, if we have a situation, equals to the density times the differential element of the volume. So I can be rewritten as the integral of rho r squared dv. And if rho is constant, if our density is constant throughout the body, we can pull that out in front of the integral. So let's develop a relationship we want to use here. Let's look at solving a problem while we do that. So let's use the shell element approach to determine our moment of inertia about the z-axis for this right circular cylinder of height h and some radius r. So we need to create a differential volume. And so what we're going to do here for that is we're going to start with a shell thickness, an elemental thickness here, of dr in the r direction. So this is the radial direction. So that will be our first spatial term, dr. Now we can get a surface area there by taking the multiplying by the circumference to pi r times dr, and then this element has a height h. So that's our differential volume, and we can certainly then easily come up with a differential mass by multiplying that by rho. Let's put the dr on last, actually. HDR. And as we said, the moment of inertia in the z direction is just r squared dm. So this is going to be this relationship where we replace dm with what we calculated from above. So now we have a integral in terms solely of r, and we can easily solve this first off by taking the rho 2 rho pi h out, and we have a pretty simple integral. So now let's think about the mass here. So the integral dm equals our mass, and that is just going to be the rho, if we have a constant rho 2 pi h times integral r dr, which ends up being just rho pi h, our value of the radius, squared. Well, we look at this relationship over here, and we can see that part of this is actually the mass. So this really equals rho pi h r squared times r squared over 2, which is just equal to m r squared over 2. And that equals the moment of inertia, the mass moment of inertia of essentially a disk of any height h. So this means a disk with a given radius of r then has a differential moment of inertia equal to r squared over 2 dm. Here you can see these are some values that you pull from a table. Here you can see this is represented right here for a disk. These are some other moments of inertia for the disk about other axes. And over on the right we see the same situation for a thin plate. Often when solving problems, it's more convenient to use a method of disks than the shell method. And there is a problem though. Say we're trying to find the moment of inertia about the y-axis here, and this is a little more complicated shape, obviously, and it's not as easy to solve with the shell method. So using a disk method, this is pretty simple to solve a problem like this, though we have to make a consideration here. So first off, let me just mention that we will be using a disk then, a disk of thickness dy as our elemental volume. And if we do this, then since the disk element here in green has a finite radius, it's all its parts don't lie on the same radial distance. So consequently, we need to first find the moment of inertia of this disk. So then again, if dm equals rho dv for our disk, that's rho times pi x squared, because this distance here is x, our radius, and multiply that by dy. That's the differential mass. But because of the finite radius, we can't just plug this into this integral here directly. So first off, we need to use that differential moment of inertia that we looked at of 1/2 dm times r squared, or essentially the x squared. So placing all this in here, we get then for our differential moment of inertia 1/2 rho pi x to the 4th dy. So we can easily integrate this. Iy then equals rho pi over 2, the integral from 0 to h here of x to the 4th dy. We need to get this into one variable, and we can do that because we have a way to convert our x. So rho pi over 2, 0 to h of y to the 8th dy. And then our answer just equals rho pi over 18 h to the 9th. Okay, let's mention some other ideas. Radius of gyration. So with radius of gyration, if we have some mass that has a moment of inertia about O, mass moment of inertia about O, so there's mass here, this is equal to a situation where we could take all that mass, lump it into this one point, and we could figure out this distance to this point here to give it the equivalent moment of inertia about O, and this we call the radius of gyration. Which we use in some applications. And that's really all I'm going to say about that. So let's talk about composite shapes and ways to find moment of inertia of composite shapes, mass moment of inertias. First, let's mention the parallel axis theorem. So if you have the moment of inertia about the center of mass, and you're looking to find the moment of inertia about some parallel axis to the axis that this moment of inertia about the center of mass and axis through the center of mass, then all you need to do is add the product of the mass times the distance to this parallel axis. And let's demonstrate this in an example problem. So say we're given this composite shape here, pinned, and we want to find its moment of inertia about O. Well, we can just use a combination of looking up moments of inertia for these different individual parts and using the parallel axis theorem to combine all this. So for OA, our moment of inertia about O taken from a table is 1/3 ml squared. So we'll just put that in, and now let's add the next part. And for the next part, we will need to use the parallel axis theorem. So using this parallel axis theorem for BC, we get 1/12 ml squares, the moment of inertia about essentially A, and then we add to that the distance to O, which is 2 feet times, and we square that times the mass. And we end up with this as 1.454 slugs foot squared.